Garage doors come in many styles, colors, and materials these days. They can be made of steel, aluminum, wood, or vinyl. Whether you choose a style that's plain or paneled, smooth or textured, a sign of quality is that the garage door is lightweight, well insulated, and airtight. The typical residential garage door is made up of 4 panels. Each one begins as a sheet of either aluminum or steel, 2 metals that can tolerate harsh climates. The side that will show has a baked-on coat of polyester paint. Depending on the model, the sheet passes through rollers that imprint a texture, such as a simulated wood grain. Then it goes through a press that imprints a design. This model will have raised rectangles. Others have horizontal stripes or no design at all. After an automated machine cuts the continuous sheet to garage door widths, another machine folds over the edges. This creates 1.5 centimeter joints for attaching the panels. The polyester paint is elastic, so it simply stretches with the bending. Now on the back side of the sheets, they hot glue metal plates to reinforce the various components they'll later screw into the garage door. Parts such as the lift handles, the hinges, and the bracket for the electric opener mechanism. They also drill a hole through which they'll later inject insulation. Now they slide 2 sheets together to form a panel. They close off the ends with blocks of pine. This will prevent cold air from penetrating inside. They apply various stickers with installation, maintenance, and safety information. Then orange stick-on dots to mark the location of the metal plates into which the installer will screw the hinges and lift handles. Now they attach an aluminum bar to the long ends of each panel. This holds the panel steady during the injection process. After injection, the bars come off. They load the panels onto a carousel and begin the process of filling the hollow interior cavity with insulation. Through the hole they drilled earlier, they inject polyurethane foam, an expanding plastic insulation material that's specially designed to penetrate hard-to-access spaces. As we see in this demonstration, the polyurethane expands and becomes rigid. This creates a solid core inside the garage door. Polyurethane is one of the lightest types of insulation, so it doesn't make the garage door heavy. Here's what the inside of a panel looks like once the foam hardens. Now, workers install various components, such as the rubber weather seal on the bottom panel. This seal prevents cold and water from entering the garage under the door. Some garage door models have windows to allow in natural light. Workers first use a high-speed router to remove the rectangles where these windows will be installed. Then they insert one of several window styles available. These are double-sealed windows, 2 thermal panes with an aluminum spacer in between. The framing around the glass is available in different colors. It's made of PVC, a synthetic resin that doesn't discolor. The frame prevents water and cold air from penetrating. Workers pack the installation hardware. Then they weigh the box to ensure no part was left out. At installation time, they attach the door panels at the joints with hinges. A system of springs ensures the garage door is perfectly balanced and moves smoothly. If properly installed, you should be able to lift or lower the garage door using just 2 fingers.
We take well-lit streets for granted, but there was a time when venturing out at night meant traveling in complete darkness. In 1814, the first gas lights lit up the streets of London, England. The first electric streetlights illuminated a public square in Cleveland in the United States in 1879. These streetlight poles are made of what's called composite, a combination of fiberglass and epoxy resin. Epoxy resin is a gooey liquid plastic mixed with a hardener. The factory constructs each pole on a mandrel, a long tapered metal cylinder. Workers first lubricate the surface. Then they take what's called fiberglass filament, a string composed of 2,200 tiny fiberglass strands. They'll wind dozens of filaments around the mandrel to create the pole. But first, the filaments go through a bath of epoxy resin. This resin is moldable, and once it's heat cured, maintains its shape. Once the filaments come out of the bath, a machine called a filament winder wraps them around the rotating mandrel. The speed of rotation in relation to the speed of the winder is critical because it dictates the angle of the fibers. The lower the angle, the more that part of the pole will be able to withstand the wind and provide constant, stable lighting. When a pole bends in the wind, the light appears to flicker. The number of filament layers depends on the design of each specific pole, and that's determined by a couple of factors. First, the type of light fixture the pole will hold. The bigger the fixture, the stiffer the pole has to be. The other factor is wind. The windier the location, the stronger the pole has to be. Once the winding's done, the mandrel moves on to the curing station. They pump pressurized steam into the hollow inside of the mandrel. The heat kickstarts the hardener in the epoxy resin. This solidifies the resin and cures it. The mandrel rotates so that the pole cures evenly. Curing time depends on the length of the pole and how many filaments it's made of. To help extract the pole, they pump cold water through the mandrel. This makes the steel mandrel contract, loosening the pole. Remember how workers lubricated the surface of the mandrel before winding the filaments? Because of that, the pole just slides off. The pole now moves on to the finishing stages. First, an automated sander works the surface. The customer can order from a choice of surface textures, from smooth to rough. Sanding takes just a few minutes. Now a saw makes a neat cut at the top of the pole where the metal tenon will go. A tenon is the component that'll hold the light fixture to the pole. This particular model has an arched mounting arm. The composite has cooled a bit since curing, so they reheat it to make it flexible. After a bending machine makes the curve, they spray cold water inside to cool the material. This registers the curve in the resin's memory, setting the bent shape. Now they cut out the hand hole, the opening through which the electrician will connect the underground wire to the fixture wiring. Workers then spray the pole with urethane paint. The paint acts like sunscreen, protecting the composite from damaging ultraviolet rays. This grommet hole will connect to the underground pipe that contains the electrical wires. After installing a cover over the hand hole, it's time to assemble the parts. The underground pipe to the pole, and the pole to the tenon and light fixture.
Adhesive tape was invented in 1925 as a painter's masking tape for auto body shops. That led to transparent tape, designed to seal the cellophane wrap used by the food industry. Then tape was introduced as a household item, and the idea just stuck. These rolls of plastic film, called polypropylene, are on their way to becoming shipping tape. The rolls go on a machine called the unwinder. Workers then position a strip of adhesive splicing tape along the end of each roll. This will enable them to connect one roll after another, creating an uninterrupted feed to the production line. Now watch closely. Once a roll unwinds completely, its end sticks onto the splicing tape at the beginning of the next roll. Once that roll's unwound, its end will stick to the beginning of the next, and so on. An automatic tension adjuster ensures that the machine pulls the film evenly to prevent ripping. The unwinder also applies a solvent to the film surface. This prevents the film from sticking while unrolling. To transform this film into tape, they coat one side with a hot adhesive known as hot melt, made from several ingredients. Synthetic rubber gives it flexibility. A UV protector keeps it from drying and discoloring, while an antioxidant prevents aging. Synthetic resin makes it sticky, while pigmentation oil provides a choice of colors, in this case, tan. They load the hot melt into a preheated holding tank, which maintains it at a piping 200 degrees Celsius to keep it from hardening. The tank pumps the adhesive to a machine called the gluer. They wipe away the excess, then roll the film. And there goes the adhesive. A cooling roller, that black one on the top, immediately hardens it. A computerized sensor ensures there's an even coat of adhesive. If not, it automatically signals the pump to adjust the output. Now, a machine called the rewinder rolls the tape onto spools. Remember the unwinder that spliced the rolls together? Well, the rewinder unsplices them. When a spool fills, a knife separates the tape at the splice point so that winding can begin on the next spool. The tape on just one of these spools would run the length of 85 football fields. The spools feed a row of sharp razor blades called the slitters, which divide the 1.5 meter wide tape into several strips. Shipping tape is 48 millimeters wide, so they get 31 strips per spool. Each strip winds onto a cardboard core, its end sealed with a tab. The length of tape per roll varies according to the customer's specifications. As the machine ejects the finished tape rolls, in comes the next batch of cardboard cores. Then it's off to the packaging department. Nothing's shipped out, however, before a quality control check. They test a sample roll from each spool. In one test, they unroll the tape sticky side up, then release a tiny stainless steel ball down an incline, measuring how far the ball rolls before it sticks and comes to a stop. To pass the test, the ball has to adhere within a certain distance. The stopping distance varies depending on the type of adhesive tape.
All consumer products are packaged, and the making of these packages starts with the burning of an aluminum plate like this one. This animation illustrates the burning process, the transfer of an image onto an aluminum plate. The plate is placed onto a cylinder, and using a laser, the burning begins. The image appears in 6 minutes. This plate will make the printing impressions on packages. The laser which did the burning has to be perfectly calibrated using this test plate. The plate is now ready to make impressions via the offset method. Printing involves ink, and it requires selecting the right one. If the desired color does not exist, it has to be made up from a mix of various other colors. An ink trial is done with a spatula. And using this small manual press, color ink tests are done. The ink is spread onto paper and the color compared with the one called for by the customer. If the two match, the presses can be started up. This is a 6-color offset process printing press with a 72 by 108 centimeter capacity. The press is fed by a suction and friction process, devouring 8,000 sheets an hour. Now the printing plate is placed onto the press cylinder. This plate will contact inking rollers of the ink reservoir. To prevent it from drying, ink viscosity is maintained with this oscillator. The press starts up and reaches a production rate of 8,000 impressions in 60 minutes. The press comprises individual color printing units. The paper sheet passes from one unit to another, receiving a new color at each step. Here they register the colors, that is, the quality of the superimposition of the different colors. The final step is the folding and gluing of the boxes. This grooved plate makes folding point marks on the carton. And this machine does the cutting, the embossing, and stripping of the sheets at a rate of 6,000 an hour. The cutting die cuts the carton sheets and, together with the grooved plate, makes the folding joints. This sheet is slid behind the cutting die to equalize the cutting of the sheets. This enormous pile of 3,000 sheets is ready to be cut. The embossing press feeder handles between 6,000 and 8,000 sheets an hour. Rollers guide the sheets in the direction of the press. And here, the sheets are embossed by the machine. The precision of the embossing is then verified. Next comes the cutting of the sheets. This goes on at 8,000 an hour. The cutting unit strips and removes the unnecessary pieces, and the carton scraps are sucked up for eventual recycling. The scraps can also be cut away manually by using a hammer. And the carton end pieces are sent off for recycling. All that remains is the assembly of the packages. This high-speed gluing unit can make up 30 to 40,000 per hour. Gluing begins with the folding of the sheets, following the folding marks. The sides of the formed box are then glued together. An average of between 5 to 8 steps are needed to fabricate a packaging box. Every day, this plant produces between 1 and 2 million boxes, requiring almost 4,000 tons of cardboard annually.